There was a time when my thoughts stood like sharpened rails. Then one evening I lay back and let them soften into distance. The noise did not vanish. It rearranged itself into a slow tide. I learned that recline is not surrender, but a new kind of attention. Light through curtains became a map, gentle and quietly legible. Breath lengthened and the room widened as if remembering its name. Memories drifted like paper boats, carrying small truths and old songs. I watched them float without steering, amazed at how gentle that was. Questions that once demanded answers softened into simple curiosities. I felt a soft border dissolve between thinking and simply being. Time slowed, not because the world paused, but because I did. This is the art of reclining. Noticing without collecting, holding without clutching. Slow swells of feeling rose and fell, each one teaching a small grace. I began to answer life with fewer words and deeper listening. Decisions became soft radiances, chosen from a wider, calmer center. There is nothing dramatic about it, only a quieter courage. When I rose, the world still moved, but my steps were softer. Great reclining taught me to return, available, awake, and kind. We call these designs black boxes, but Apple Silicon opens that box. It rethinks chip architecture from isolated parts to a unified system. That shift affects performance, energy, security, and software design. Today we'll map the architecture and explain why it matters. No marketing, just an engineer's view on architecture and trade-offs. Let's start with the core building blocks inside the package. Modern Apple chips pair high-performance cores with efficient cores. A tightly integrated GPU accelerates graphics and parallel compute. Dedicated neural engines handle machine learning with deterministic throughput. Unified memory removes data copying, reducing latency and power. A high-bandwidth fabric connects cores, memory, and accelerators coherently. A hardware enclave provides isolated cryptographic security services. Performance per watt improves because communication costs are dramatically lower. Co-designed silicon and software yield predictable performance and latency. Developers can exploit unified memory and specialized engines directly. Control over silicon, OS, and apps enables tighter optimizations. Hardware roots of trust protect data without constant software overhead. The result is devices that feel faster, cooler, and longer lasting. This architecture scales across phones, laptops, and desktops efficiently. New accelerators will arrive as workloads evolve, like media and AI. Toolchains and compilers must adapt to expose hardware capabilities. Ecosystem alignment reduces fragmentation and simplifies cross-device experiences. Apple Silicon is not magic. It's an engineering trade-off with measured gains. Understanding the architecture reveals why it truly changes everything. We call it the air-gapped oracle, a sovereign cognitive engine for critical systems. Built to think without exposure, it separates intelligence from connected networks. Today we examine why air gaps matter and how they are implemented. Minimalist diagrams reveal layered defenses, hardware, enclaves, one-way data flows, and physical seals. Our journey traces architecture, workflows, and the compromises engineers accept. Listen for defining terms that clarify the system's components and guarantees. At the core lies an isolated compute enclave, immutable and auditable. Data arrives via controlled import channels, curated and cryptographically attested. One-way guards move only approved inputs into the enclave. Inside, models run deterministically, joined by a verifiable ledger of operations. Outputs leave through export mediators that strip provenance and enforce policy. This layered choreography balances autonomy, reproducibility, and accountability. Air gapping reduces attack surface, but imposes latency and limited data scope. Operators must design for robustness, reproducible training, signed updates, and human oversight. Schematic animations show fault-tolerant replication and offline verification cycles. Physical controls matter: tamper-evident seals, hardware root of trust, and audited facilities. Threat models shift from remote exploitation to insider risk and supply chain attacks. Mitigations combine cryptographic attestations, redundant checks, and policy-driven export filters. Sovereign cognitive engines promise resilient decision-making for critical infrastructure and defense. Yet, they require governance frameworks that match technical guarantees with legal accountability. Researchers explore verifiable AI, reproducible pipelines, and standardized attestations. Ultimately, sovereignty is social as much as technical: trust, transparency, and oversight. The air-gapped oracle is not isolation for its own sake, but controlled autonomy. Its design asks a simple question: how do we build intelligence we can trust? Every digital system hides a secret, an invisible force shaping what can be known. We call it privacy, but it's more than choice. It's a physical constraint. Like gravity, privacy imposes limits on measurement, transfer, and observation. Data flows, sensors probe, algorithms predict, yet some information remains fundamentally uncertain. This uncertainty isn't failure. It's a law that protects space for individuals and society. Today we explore privacy as a physical law, precise, unavoidable, and deeply practical. Measurement changes systems. Observing data alters the system you hope to study. Every query leaks structure, every share reduces the unknown. Mass surveillance treats data as unlimited fuel, ignoring the cost of disclosure. The result: fragile trust, brittle institutions, and hidden harms that grow undetected. We need a model that treats privacy like conservation, not an optional setting. That model reframes disclosure as a resource, conserved and quantifiable. Think of information as energy and disclosure as work performed on a system. Each interaction expends privacy. Cumulative queries can deplete an individual's secrecy. Mathematical tools quantify this depletion, limits, trade-offs, and recoverable uncertainty. Techniques like differential privacy enforce bounds, like walls that limit measurement. Cryptography, decentralization, and minimal collection are engineering ways to respect these bounds. Designing systems with built-in constraints makes privacy predictable and auditable. Treating privacy as law shifts responsibility from users to system designers and policymakers. It demands transparency about what measurements are possible and what remains unknowable. Companies must report privacy budgets. Researchers must account for information costs. Regulators can enforce conservation principles, balancing utility against inevitable leakage. If we accept privacy as physical, we can build technologies that honor human dignity. Choose systems that limit extraction. Demand designs that treat privacy as fundamental. Silicon systems underpin modern life, yet their complexity creates hidden technical risks. This video maps those challenges and outlines practical, technical paths forward today. We examine scalability limits, hardware bottlenecks, supply fragility, security gaps, and observability. Visual charts will quantify impact and highlight where engineering effort matters most. Expect concise analysis, subtle, futuristic visuals, restrained palette, and deliberate pacing throughout. First, we assess core technical constraints across silicon manufacturing and system integration. Manufacturing yields remain variable, driving cost and availability uncertainty for advanced nodes. Wafer defects, lithography limits, and material impurities reduce effective production capacity significantly. Supply chain concentration amplifies risk when single-source suppliers encounter disruption globally today. Power efficiency limits and thermal density constrain performance scaling in data centers. Security vulnerabilities persist across firmware, side channels, and supply chain tampering vectors today. Observability gaps hinder diagnosis. Telemetry blind spots make root causes hard to isolate. Improving yields requires tighter process control, advanced metrology, and adaptive manufacturing feedback. Diversifying suppliers and strategic inventory buffers reduce risk from localized disruptions significantly. Designing for observability means instrumenting silicon with secure, low-overhead telemetry points everywhere. Security must be layered. Hardware roots, verified firmware, cryptographic provenance, and runtime checks. Energy-aware architectures and dynamic thermal management unlock sustainable performance scaling for centers. Collaboration across industry, academia, and standards bodies accelerates practical, interoperable solutions quickly. Short-term, prioritize resilient designs, improve telemetry, and contingency supply plans now. Medium-term, invest in manufacturing R&D, secure architectures, and cross-vendor interoperability programs. Long-term, pursue new materials, heterogeneous integration, and verified energy-efficient computing models. Metrics matter, track yield variance, mean time to detect, and energy per computation closely. The path forward balances pragmatism with innovation to sustain progress in silicon systems. Together, the ecosystem can navigate the silicon labyrinth and build resilient futures.